In this lesson, we're going to talk about how we can use the mental ray physical light. So this physical light can be connected to any of your Maya lights, just like all the other mental ray light types. So in this case, we can use just a simple area light, or again, any kind of a Maya light will work. We can select this, take a look inside the attributes, and go down to the mental ray tab. Scroll down, and inside the light shader, we'll connect up the physical light. So let's go over to the mental ray tab, scroll down, and connect physical light. Now you can see that there are just a few attributes that are responsible for this, but let's just take a quick render to see what we have. Now you'll notice that once we render, that we have very close to this point source, or this point of light emission, that everything is very, very bright, especially right around here. You can see this very distinct hotspot. But once we move out past that area, you can see that our illumination is much more even. Now this physical light is actually based on real light physics. So let's take a look at a quick graph that will illustrate this point. And to show this, I've just worked up a fairly simple graph. So on the column on the left, we have light intensity that goes from a value of 0 to 1. And then at the column along the bottom, we have distance. And in this case, just for simplicity's sake, I'm using a purely arbitrary distance to illustrate this. So in actuality, light in real life does not fall off in any kind of a linear pattern from the point of emission to the distance at which that light's no longer visible. That light does not fall off in a straight line. Instead, light actually decays according to something called an inverse square rule. So if we were to take this distance, and again, this is just a purely arbitrary distance for simplicity's sake, but if we were to split this into equal distances or equal units, what we'll see is by the time the light reaches that first unit of distance, it's decayed by about half of its value, so it's lost roughly half of its original intensity. Now by the time the light traverses to that next unit in distance, it's now lost half of its previous value. And you can see that that pattern continues on and on and on until the point where we really don't see the light anymore at all. So what that means is in real life, as we are very, very close to the light source, we'll get very, very bright lights. But very quickly, once we move away from that point of emission, you can see how our light will really level off and become much more even. That is really what inverse square means, and that's exactly the kind of a fall-off pattern that this physical light is designed to simulate. So you can see that this physical light behaves very similar to something like a point light, in that we have light that's being emitted out from 360 degrees and illuminating all around. But you do see that we have that very distinct pattern that we just looked at in the graph, where our light source is very, very bright as we're very close, but very quickly that light falls off and becomes much more even. So because this is actually based on some kind of a real-world unit of fall-off, if we're going to be using some kind of a physical light, it will work best if we ensure that our scene is modeled out to some sort of real-world scale. So normally if this were something that we're going to be modeled out, let's say an interior of a room, you would want to make sure that your interior is modeled to some kind of a real-world meter type of measurement. We can set that up in the Maya units. So as far as this physical light goes, again, there are just a few attributes that control this. You will notice that there's no attribute that controls the intensity of this light. Instead, that intensity is derived from the color. So if we were to click on this, you can see that right now the color value is set to a value of 1000. Now this is controlling the overall intensity of the light, so if we were to drop this down, and say to a value of 100, and re-render, you can see now that our light is much less intense. So if we were to kind of imagine that this light were right up in this area where my cursor is, you can see that now by this point it's now really lost a lot of its original intensity. So at this point now we have a much more even lighting effect. Again, because by the time the light reaches this area, we've now pretty much bypassed that initial spike in intensity as the light was coming from this emission source. So below that we have the cone. Now this is really referring to the cone angle that we would see if this were a light connected to a spotlight. So since it's not connected to a Maya spotlight, this particular attribute is really not useful for us. Now the threshold below this is really a cutoff point that we can define for the overall intensity of the light. So right now, if we were to set the threshold, let's say to a value of 0.1, Now, any light that falls below this threshold will be discarded. And if we take a quick render, you can see that that's exactly what we get if you compare what we had before to what we have now. You can see that the illumination that we would have received back in this area falls below that threshold value of 0.1, and so as a result, that illumination from that light is thrown away. So this can sometimes help to speed up your renders if you need to have some kind of a cutoff point. Now the cosine exponent, this really applies to the area light. Now this is, in our case, what we're using as our emission source. So the cosine exponent, if we were to start to increase this, this will now start to drive more the illumination of this physical light to sort of an inner area that is defined by this area light. So this will become a little bit more apparent if we were to take this light and maybe move this back a little bit. And we should now start to get a little bit more of a focused directional effect to this physical light. So we can begin to see that effect happening just a little bit. If we were to rotate this back. And let's maybe try to lower this down a little bit so this should become really apparent now. Just to make this a little bit more apparent, we can begin increasing this value back to its original level of 1000. That should make this effect a little bit more visible. Now you can see that even though we have the light positioned in some kind of an angle, that even though the shadows are behaving according to that angle, that we really still don't get the actual light fall off or the directionality of the actual light source itself based on the area light. So there is actually one more option that we need to enable in the area light. So if we take a look inside the area light options themselves, if we scroll down just underneath the Maya area light tab, we have the option to use the light shape. Now if this is set to either a rectangular area light or a disk area light, now we can utilize that cosine exponent that we just set. So use light shape, set the type to rectangle, go back to the physical light, make sure we have our cosine exponent set up to some kind of a sufficiently high value, and let's re-render. And now you can see that this physical light is able to take its light direction and base that on the orientation of the area light. And you also see that once we enable that option, that we start to get some of these nice soft shadows from the area light as well. So a lot of times, again, whenever using this physical light, it does become very important to try to model your scene to some sort of a real-world scale so that you can try to avoid these hot spots as much as possible. However, that may not always be an option, so a good way to fix these hot spots is to utilize some kind of a lens shader, such as the simple exposure or the photographic exposure. So if you want to learn more about how we can start to eliminate these hot spots, you can refer to our lesson on using the Mental Ray simple lens exposure. So that's a look at how we can utilize this physical light.